Hello, this is Professor Roman. We'll continue our lectures on linear algebra. We've just studied the natural projection map. If S is a subspace of a vector space V, then the natural projection pi sub S maps V to V mod S. Pi sub S sends a vector little v to the coset V plus S. We have seen that this is a surjective linear map whose kernel is the subspace S. This map is quite important. It will give us considerable insight into the subspace structure of the quotient space V mod S, the subspace lattice of V mod S. What do the subspaces of V mod S look like? Well, it certainly would seem that they should relate somehow to the subspaces of V. If T is a subspace of V that contains S, so T sits between S and the entire vector space, we can form the quotient space T mod S. T is a vector space in its own right. S is a subspace of T as well as of V. And T mod S is easily seen to be a subspace of V mod S, because if we take two vectors in T mod S, so T1 plus S and T2 plus S, and we form a linear combination of those vectors, those cosets, coset arithmetic allows us to write this, and this should be a T1. A T1 plus B T2 belongs to capital T because capital T is a subspace, and so the coset belongs to T mod S. The real question is whether or not there are any other subspaces of V mod S besides those of the form T mod S, where T is a subspace of V that contains S. And we're going to see that the answer is no. These are all of the subspaces of V mod S. Let's denote the family of all subspaces of V that contain S using this notation, sub V semicolon S. So this is all the T, the subspaces that lie between S and V. And we'll refer to these subspaces as intermediate subspaces between S and V. So we have shown that if T is an intermediate subspace, then T mod S is a subspace of V mod S. Here's a picture. Here's V. Here is the trivial subspace. Here is the subspace S. The intermediate subspaces lie between V and S. The natural projection, I probably should have labeled this pi sub S, sends T to T mod S. There is one word of caution with respect to this figure. The subspace lattice of a vector space, generally speaking, is not totally ordered. So there'll be subspaces over here and over here. The Hasse diagram of the subspace lattice may be quite complicated. So this figure with just the straight lines here is a little bit restrictive or misleading. All we care about at this moment is an individual subspace that lies between V and S. So the projection map, pi sub S, which sends V to V mod S, induces an order isomorphism, which I will denote by pi bar of S, that sends the intermediate subspaces, the subspaces of V that contain S, to the subspaces of the quotient space V mod S. And it sends the subspace T, the intermediate subspace T, to T mod S. We discussed order isomorphism some time ago, and so if it's not fresh in your memory, it might be a good idea to pause this video and go back to that discussion. Or if you have the book, to take another look at Appendix B, where you'll find a discussion of order isomorphisms. Here is the definition to refresh your memory. We have two partially ordered sets. A function f from P to Q is said to be order preserving, also called monotone or isotone, if for all x and y in P, x less than or equal to y implies f of x less than or equal to f of y. This is order preserving. A function f from P to Q is called an order isomorphism if it is bijective and if x less than or equal to y holds if and only if f of x less than or equal to f of y. So this is a biconditional. This is simply a conditional. So what we are going to prove is that given a subspace S of V, there's a bijection. Let me get these pages separated. A bijection between the intermediate subspaces, between S and V, and all subspaces of the quotient space. And this is the bijection. T maps to T mod S and vice versa. Well, in particular, this means that all the subspaces of V mod S have this form, T mod S, for some intermediate subspace T. But that's not the end of the story. The bijection is order preserving in both directions. It's an order isomorphism. So T1 less than or equal to T2 if and only if T1 mod S, this is a subspace. The order here is set inclusion, but because these are subspaces, this is also, the order is also subspace order. So T1 is a subspace of T2 if and only if T1 mod S is a subspace of T2 mod S. The formal statement of this, that the natural projection induces an order isomorphism, is called the Correspondence Theorem. And here's the formal definition. S is a subspace of V. The natural projection pi sub s maps V to V mod s. The induced map, sending t to t mod s, is an order isomorphism. That is to say, it's a bijection with this property. As to the proof, first, to see that pi bar is injective, and then I should say this picture is something well worth imprinting in your mind. I'm sorry I drew this extra stuff on there. You can ignore that, although the label pi sub x is something I should have put on there. Intermediate subspaces get mapped to subspaces of V mod s, and this is a one-to-one correspondence between these subspaces up here that contain S and all the subspaces of V mod S, and it preserves order, it preserves set inclusion. Okay. So to see that pi bar is injective, we have to show that if T1 and T2 are intermediate subspaces, then T1 mod S equals T2 mod S implies T1 equals T2. Okay, this is the image of T1 under pi bar, and this is the image of T2 under pi bar. So if the images are equal, the pre-images have to be equal. That's the definition of injectivity. But if little t1 is a vector in big T1, then the coset T1 plus S belongs to T1 mod S, which is equal to T2 mod S. And so there's a vector in T2 for which the coset T1 plus S is also equal to T2 plus S. This whole coset is contained in T2 because S is contained in T2 and little t2 is an element of T2. So therefore, again, S is in T2, so T1 is in T2. Okay. So that gives us the inclusion T1 is contained in T2. But we can reverse the roles of, this is a symmetric argument, we can reverse the roles of T1 and T2 and get the reverse inclusion, so T1 is equal to T2. And the induced map is injective. As to surjectivity, we have to show that every subspace of V mod S, call it X, has this form, X equals T mod S, for some T that belongs to this family of intermediate subspaces. It's the domain of pi bar. Well, the elements of X being a subspace of V mod S, they are cosets of S. And so, of course, they're subsets of the vector space V. A coset is a subset. So we can take the union of all of the cosets in X, all the elements of X. So it looks like this. Another way to say this is simply the set of all coset representatives of all of the cosets in X. Every element of a coset, as you know, is a coset representative. So we take the union of all these cosets, we're just throwing all the coset representatives into a big set, T. T is in fact a subspace of V. And here's the proof. If U and V belong to T, then that means that U and V are coset representatives for cosets in X. So U plus S is in X, and V plus S is in X. And therefore, this linear combination of these two cosets, an arbitrary linear combination, also belongs to X, because X is a subspace of V mod S. This can be written this way. It's coset arithmetic. So this belongs to X, which means this vector in the parentheses here is a coset representative for a coset in X. Therefore, it belongs to T. And so T is closed under linear combinations. And therefore, it's a subspace. Being a subspace, it does contain the zero vector in V mod S, which, as you know, is S itself. So S is a member of X, and therefore a subspace of T. It's part of this union that defines T. So T belongs to sub Vs. It's a subspace of V containing S. To show that our subspace X is in fact equal to T mod S, which is the image under pi bar of T, that will show us that pi bar is surjective. First, observe that if V plus S is a coset of X, an element of X if you want, then V is a coset representative for a coset in X, and so V is in T. So if V plus S is in X, then V is in T, which means V plus S is in T mod S. So X is contained in T mod S. For the reverse inclusion, if little t plus S is in T mod S, where little t is in the subspace T, then T is a coset representative for a coset in X, and so T plus S is in X. So any coset, any vector in T mod S is also a vector in X, so we have the reverse inclusion. T mod S is contained in X, so they're equal. So pi bar is not only injective but surjective. It is a bijection. Finally, we have to show that it preserves order in both directions. If we have two intermediate subspaces, T1 and T2, then certainly if T1 is contained in T2 or is a subspace of T2, then T1 mod S is a subspace of T2 mod S. That's straightforward. For the converse, if T1 mod S is contained in T2 mod S, we have to show T1 is contained in T2. Take a vector little t1 in T1, then there has to be a vector T2, little t2 in T2 for which these two cosets are the same. And so T1 is equal to T2 plus S, little s, for some little s and capital S. And since capital S is contained in T2, we deduce that T1 is a vector also in T2, and so T1 is contained in T2. I would suggest the correspondence theorem is very important. It gives us a complete description of the subspace lattice of a quotient space in terms of the subspace lattice of the original vector space. This is an important theorem. I suggest you spend some time with it, see if you can construct the proof yourself, see if you can improve on the proof. The correspondence theorem has versions in group theory and in ring theory. So it's a common theorem in abstract algebra. Example, the correspondence theorem tells us that the subspaces of this quotient space, this is the polynomial space, factor out the subspace of polynomials of degree 3 or less. The subspaces of this quotient space are in order-preserving bijection with the intermediate subspaces. The subspaces of the polynomial space that contain F3 square bracket x. And this is the map. So for example, this is an intermediate subspace. The subspace spanned by 1x, x squared, x cubed, x to the 5th, x to the 23. This is the this group of vectors there guarantees that F3 square bracket x is contained in T. I just stuck those in randomly. Could be anything. Pi bar, the projection map, the induced projection, sends this subspace to its quotient space. When you factor out by F3 square bracket x, you get these cosets. This is a linear combination of these two vectors. The vectors in T, of course, are linear combinations of all these vectors, but the portion of the linear combination that involves 1x, x squared, and x cubed gets absorbed into the subspace. There is a group of 3 theorems in linear algebra that concern the existence of certain linear isomorphisms, unlike the correspondence theorem, which concerns the existence of an order isomorphism. Naturally enough, these 3 theorems are called the Isomorphism Theorems. And actually the correspondence theorem is sometimes referred to as the 4th isomorphism theorem, although, as I said, the correspondence theorem concerns an order isomorphism as opposed to linear isomorphisms. The first isomorphism theorem is actually the father of the other 2. And it goes like this. Any linear transformation tau from V to W induces an injective linear transformation on the quotient space V mod the kernel of tau to W. And it's defined, I call it tau bar on a coset V plus kernel of tau is equal to tau applied to the coset representative. So in fact, if we restrict the codomain to the image of tau, then the resulting map, tau bar, is an isomorphism between the quotient space V mod the kernel of tau and the image of tau. So in words, we could say that if we factor out the kernel of tau, that produces a quotient space that is isomorphic to the image of tau. Very important theorem. As to the proof, the first step is to show that tau bar is well defined. We've had a lengthy discussion about this issue. When you try to define a function on a quotient space by using coset representatives, we have to be sure that the definition does not depend on the choice of coset representative. So, if we have two coset representatives, v and u, for the same coset, then these cosets are equal, which means the difference, v minus u, is in the subspace, in this case the kernel of tau. So tau of v minus u is 0, which means tau of u equals tau of v, and so this is well defined. Next, we have to show that tau bar is linear. So just for convenience, we'll write the kernel of tau as k. So we apply tau bar to a linear combination of two cosets of k. That's equal to tau bar of, by coset arithmetic, these can be combined. Then we, by definition of tau bar, this is tau of au plus bv. Tau is linear, so we can write this, which by definition of tau bar is equal to this. Finally, we need to show that tau bar is injective, so we need to look at its kernel. If tau bar sends a coset v plus k to 0, that's the same as saying tau of v is 0, or in other words, v is in k, and so v plus k is the 0 coset k. And that's the proof. So the proof is relatively simple, straightforward at least, but yet this theorem is more important, you might say, than the proof seems to indicate, than the simplicity of the proof seems to indicate. The other two isomorphism theorems are direct consequences of the first isomorphism theorem. So to sneak up on the second isomorphism theorem, let's assume first that a vector space V is a direct sum of S and T. Then the other projection maps, not the natural projection, but these maps we talked about a while ago, rho st, that map V to S defined by dropping the T component of a vector, is a surjective linear map from V to S, and its kernel is T. So the first isomorphism theorem tells us that, in this case, V here, S plus T, mod T is isomorphic to S. That's a very pleasing formula. It's almost as though these were numbers and you could actually cancel. You can't, that's not what they are, of course, but it's a nice formula. It's a pleasing formula. It should be easy to remember. But what do we do if S and T are not essentially disjoint? What if this sum is not direct? Then this map is no longer well defined, because a vector may have two different S components, and this definition depends on the choice of S component. But we can correct that problem by changing the codomain. See, we can eliminate the problem of non-uniqueness of S components. We factor S by the intersection, S intersect T. And the reason this works is that if a vector has two different projections, so if V is S plus T and also S prime plus T prime, where the S's belong to capital S and the T's belong to capital T, but if S and S prime are different, or maybe I should say regardless of whether they're different or not, we have S minus S prime equals T prime minus T, and so this vector belongs to the intersection. So in particular, S minus S prime belongs to the intersection, and so these two cosets are the same. So we've eliminated the problem of ambiguity of different coset representatives giving different results. So officially then we can define a map tau from V to this quotient. Tau of S plus T is S plus the intersection. So that differs from the original projection map. We're going now into quotient space. But this is now well defined. It is also surjective, and its kernel is still T, and I'm going to leave that for you to verify. So this is now what an application of the first isomorphism theorem looks like. S plus T, which is V, mod the kernel isomorphic to the image. This is the second isomorphism theorem. So this one's a little trickier to remember. When you take S plus T and you factor out T, you don't necessarily get something isomorphic to S, but it is isomorphic to S mod the intersection of S and T. So when S and T are essentially disjoint, factoring out by the trivial subspace does nothing really. It's isomorphic to S. For the third isomorphism theorem, start by supposing that we have two subspaces, S and T of V, and S is also a subspace of T, so this is a hierarchy of subspaces. We can define a function from V mod, the smaller one, S, V mod S, to V mod T by taking an S coset represented by V and using V as a representative of T coset. So swap S for T. This is well defined precisely because S is a subset of T, so that if you have two different expressions for the S coset, for an S coset, V plus S equals V prime plus S, then V minus V prime is in S, and the point here is that that's also therefore in T, and so the T cosets are the same. This argument would fail if we tried to go in the other direction. Also, this map is surjective, and its kernel is the set of all S cosets whose corresponding T cosets are 0, in other words, equal to T. So V plus, this is v plus t equals t if and only if v belongs to t. So it's these cosets, which is t mod s. This is a legitimate quotient space. T is a vector space and S is a subspace. So the first isomorphism theorem tells us that the vector space divided by the kernel of tau is isomorphic to the image of tau. So V mod S factor out the kernel T mod S is isomorphic to V mod T. This is the third isomorphism theorem, and again, this can be remembered by thinking of these as fractions, and you can then cancel the s's. We have to be very clear, though, this is nothing more than a simple way to try to remember this expression. There's no such thing as cancellation of subspaces. Well, not in this context. Actually, we'll talk about that. I think that's coming up in the future. Cancellation in a direct sum. Sometime in the distant future. So that is the story on the three isomorphism theorems. They will prove to be quite useful from time to time, especially the first isomorphism theorem is quite useful. The other two are a little more specialized, obviously.